Now we will talk about convergence in Markov chains. We know from the Chapman-Kolmogorov equations for the homogeneous case that the probability of transitioning from state I to state j in n plus r steps is given by summation over k over the state space pik transitioning from I to k in n steps times the probability of transitioning from k to j in r steps. Now take n and r as 1, for example. Pij2 is equal to summation pik pkj, because these are the one-step transition probabilities. Now, what does this tell us? This summation is really a vector product, a dot product of these two vectors, I1, Pi2, and so on, multiplied by P1j, P2j, etc. What this also is the ijth entry of the transition probability matrix multiplied by itself. Okay. In general, by extending from this, by iterating the same arguments, you can easily show that the probability of going from I to j in n steps can be given by the ijth entry of the p to the n matrix. In general, the matrix of pij n values is given by the transition probability matrix multiplied by itself n times. Okay, so let's talk about a probability vector then that evolves in time. Define the vector mu as the vector of probabilities, the probability that xn is 1, the probability that xn is 2. Remember, our state space is the state of is positive integers, either a finite or we're talking about a countable state space, does not have to be finite. For the moment, to make things easy, you can think of a finite state space, but these definitions work for the countable case. Okay, so think of this finite size probability vector at time n. This is the vector of probabilities of the process being in each state at time n. So we're interested now in how this probability vector evolves. Let's call this mu n actually. And by this argument, it's easy to show that mu m plus n is equal to mu m multiplied by p to the n. So a very valid question then is whether this probability vector converges to something as time increases. So as m increases, in other words, as n increases, as we're multiplying p many times by itself, does it converge to something such that the probability mu m and the probability mu m plus n are roughly the same vector? We say then the Markov chain has converged to a steady state distribution. So let's explore this. Perhaps we can explore this on an example. Okay, so let our example be this sort of dire example of a random walk next to a cliff. Random walk on the edge of a cliff. Okay, so here's the setup. position 1 denotes the basically right after the edge of this cliff. Position 2 is here, position 3 is here, and position 4 is here. Okay, and we're doing a random walk without looking at the cliff, or without trying to avoid falling off the cliff. And if we come to position 1, it means we fell off the cliff. So, so think of some particle moving between these 4 positions. And if the particle is in state 1, it means it fell off the cliff, so game is over. Once it reaches state 1, it will stay at state 1. If it's in state 2, it will move to state 1 with probability 0.3, and it will stay in place with probability 0.4, and it will move to the right to state 3 with probability, to the left to state 3 with probability 0.3. Okay, notice that these probabilities add to 1 as they are the row sum of the transition probability matrix, or by total probability theorem, depending on how you would like to see it. If the particle is in state 3, it will stay in state 3 with probability 0.5. It will move to state 4 with probability 0.5. Okay, either this or that. And if it is in state 4, it will stay in state 4 with probability 0.5. And it will move to state 3 with probability 0.5. So we can ask a number of interesting questions on this very simple example. For example, given that the particle started in a particular state, what is the probability that it will fall off the cliff? What is the probability it will never fall off the cliff? How long does it take, given that it started in a certain state, how long does it take to fall off the cliff? Or does it matter what state it starts in, etc. So let's try to answer some of these questions. First of all, let's write down the transition probability matrix P. In this case, P, the first row of P is 1, 0, 0, 0. The second row is 0.3, 0.4, 0.30. And the third and fourth rows belong to states 3 and 4, then they're identical, 0, 0, 0.5, 0.5, 0, 0, 0.5, 0.5. Okay, so that's the matrix of one-step transition probabilities. How about the matrix of two-step transition probabilities? We know that two-step transition probabilities are obtained by multiplying the matrix P by itself. So P squared is then P times P, which is, well, the first row, when you multiply, you still get the same thing, essentially, 1, 0, 0, 0. The second row is going to change, 0.42, 0.16, 0.27, 0.15, and the third and fourth rows also do not change. Clearly, it is easy to see that they are not going to change when we repeat this process for a second time when we compute three-step transition probabilities. When we compute three-step transition probabilities, we get 1, 0, 0, 0, 0.468, 0.006, 0.25, 0.21. Let me redo this. And 0, 0, 0.25, 0.25, 0, 0, 0.25, 0.25. sorry, this is of course 0.5, 0.5. Let me fix this. 0.5, 0.5, 0.5, 0.5. Okay. Now, from here, we see a number of different things. Maybe first let's look at the limit. The limit as n goes to infinity, p to the n, is 1, 0, 0, 0. What do you think this is converging to? This seems to be converging to 0.5. 0.5, this seems to be converging to 0, and it does really converge to 0. 0.25, 0.25, 0, 0, 0.5, 0.5, 0, 0, 0.5, 0.5. So this is the limit of p to the n as n goes to infinity. What does this mean? We're taking n to infinity here on both sides. So this means that the p to the n matrix converged to some p infinity matrix. And let's see how what this implication of this is that the probability vector has converged as well. So this means that if you look at here, this first row belongs to state 1. And this means that the probability of transitioning from state 1 to 1, the probability that you are in any state, given that you start in 1, is 0, except for state 1 itself. Okay. Now, how about look at this column here. This column means that no matter where we start, no matter which state we start at, okay, we are not going to end up in state 2 eventually, okay? In the next lecture, we will give the formal definition of a transient state. But this is an example of a transient state. It is not going to be visited eventually. We will stop visiting this state. So the probability of visiting the state infinitely often is 0. Okay. Let's look at this particular group of numbers. This says that given that we are in states 3 or 5, we are equally likely to be in 3 or 4 in the next state. So basically in the next step. So basically this signifies that 3 or 4 are a recurrent class, which we will define formally in the next lecture. Okay. Of course, state 1 is a recurrent class itself as well. Okay. State 1 is a recurrent class by itself. So this 1 here shows that state 1 is a recurrent class by itself. And we call this kind of recurrent class with only one state an absorbing state. State 1 is an absorbing state. Once you get into state 1, you never get out of state 1. Okay? Now let's notice something. Basically, p to the n P infinity, this P infinity matrix is the matrix of the limit as n goes to infinity Pijn, right? The limiting probabilities or the eventual steady state probabilities. Note that these steady state probabilities given in this matrix depend on I. So for each j, the eventual probability of being in J after an infinite number of transitions depends on where we started. No matter how many transitions there have been, where we originally started still matters. This is because in this Markov chain there are more than one recurrent classes. Okay, so this is an example of a non-ergodic situation, and we will formally define all of these in the coming lectures.